Everyone, it's April the 6th. Alright, so I may not have much time. I'm waiting for my car to be ready. So if the uh, if Tire Kingdom calls me, I have to go. But anyway, let's just try to solve this problem. Three sum with multiplicity. If we have time, we have to take a look at this Z algorithm stuff to solve that difficult problem. Alright, let's try to take a look at this one first. Three sum with the multiplicity. Oh, we've done this before. When did we do it? Back in March 2021. Okay. So given an integer array and an integer target, return the number of tuples such that I, j, k, and then these three added together equals target. Okay. So target is 8. 1, 2, 5. 1. Oh, hold on. It's I0, 1. Oh, no. This is actually counting the values. So we want to find what? The number of tuples that can make it. So 1, 2, 5. And duplicates can have, because I have 2 1s, 2 2s, and 2 5s. 1, 3, 4. 2, 3, 3. Nice. Length is 3,000. Okay. What was the idea? Well, what we can do, it's a three-sum problem, right? That means, we can first do a counter on them, right? We do a counter on them, so we can reduce the problem to, like the first example would just be 1, 2, 3, 4, 5, and each one we have a number attached to it. So we can say, all right. So we're gonna first try to find three values. It's all different, right? We can have three distinct values. Is the most of three distinct values, or two distinct values, or one distinct value. So three distinct values. That's a three-sum problem. So we do. How do we do three-sum problem? We locate one value, right, and then it becomes a two-sum problem. So basically, we record two values, like we record 1, 2, and then try to find if there is a 5. We have a 5. Boom, done. And then we do 1, 3. Try to find if there's a 4. There's a 4. If I have 1, 4, and we need a 3. Well, we already considered, so we don't consider again, right? So yeah, we can sort it, right? We sorted it, so once we cross half line, and that's it, right? Once we cross half line, so 1, 2, 2, 3, 1, 2, 1, 3, right? It haven't crossed the half line yet. Yeah, if it's anything like it's smaller, right? We have to find it to the right side, right? If there's anything smaller, we're doing it already. So 1, 2, 1, 3, 2, 3. 2, 3 needs 3. Oh, we can actually just do that. 2, 3 needs 3. Okay, so 2, 3 needs 3. So we have 2, but 3 needs, I need 2 3s, right? So we're looking at 3, and that is a combination, right? So however many 3s I have, I just need to pick 2. Yeah, it's all combination, right? It's all combination. It's just this choose 1. Some is choose 2. So maybe we can make it the solution generic, right? 2, 3 we done. 2, 4. 2, 4 we go back to the 2, which is actually right. 2, 4 we can. So if we go back, it has to be. If we go back, it has to be on itself, but cannot be from on other values, because if it's it's other values, then we must have handled it already. So it has to go back. Then everyone we should first check itself, because we might have the same numbers. So each one check itself, see how many we have, right? And then see if we can make to the target by taking the same value multiple times, right? By taking the same value multiple times. Yeah. So each value, so we take one time, take two times, or take three times. If we take like each number, if we take three times, then we just try to see if we can make it, right? And we can take two times, and that becomes a two-sum problem, right? If we take one time, and then it becomes a three-sum problem, and then if we take one time, we just go for the next one, and then yep, I think I have a solution for this. Let's see if we can do this without error, because last time I saw I had an error. All right, so what do we say? We say do like this. All right, so we need a counter. All right, we say from collections import counter. Okay, so I have a counter. We say counter equals to counter array, right? And then for, and then key nums. And say sorted counter, right? And then we're gonna go from one by one, right? And say for I and enumerate nums. Perfect. Enumerate nums. Now what? So for each num, we're gonna try take it three times. So take three times. All right. We say if counter n is larger or equal to 3 and 3 times n is equal to target. All right, rest plus equal to something. All right, we have a rest equals 0, and we have a mod. Mod is going to be what? I think it's 1. I can do 1e, right? 1e9 plus 7. So rest equal to rest plus how many? So C. So that should be counter n times choose 3, right? N choose 3 shall be n factorial 3 factorial n minus 3 factorial, which is n times n minus 2 times n minus 3 divided by 1, 2, 3, 6. Okay, so this will be this times this minus, right, this times this minus 1, right, minus 1, come on, times this minus 2, right, and divided by 6. So rest equals rest plus this mod. Okay, so that's we know what this is doing. So next is 2 times. We say if counter n is larger or equal to 2, right, and 2 times n is smaller than target, right? Because value is 0. Value is 0. That means we can get to 0. So let's do smaller equal to. Right, smaller equal to. But if we sorted it, 0 will go first. So when I do 2 sum, I don't look to the left, I only look to the right. So actually smaller shall be right. Because smaller equal to, which means I can do 0, but I cannot do 0, right? So if it's smaller than target, then the goal is to find if we have anything, right? So it's a 2 sum problem. We say if so new target, new t equals target minus 2 times n, right? I'm going to say if new target is in counter and new target is larger than n, right? Then res equal to res plus, now it's choose 2, so it's this thing, right? Now divided by 2 and plus, is that plus? It's not plus, it's divided by 2 times. There's a number of times I can choose 2 and a number of times I can choose, so we counter new t. Okay, so that's the second one. Yeah, it has to be larger than n, right? And the third is if counter, well, we're doing counter definitely larger equal to 1, and if n is smaller than target, right? If n is smaller than target. If n is larger than target, we cannot do anything. So new target equals to target. Actually, no, in this case, we're just going to, let's say j equals, so we do, it has to be 3 individual, right? Because if those we have, oh, hold on, maybe we can do, so like if I take 1, yeah, they have to. So okay, so j will equal to, I don't know, I plus 1, right? And then what? And that's a 2 sum problem. That's a 2 sum problem. Aren't we doing the same thing over and over again? Yeah, we're doing the same thing over and over again. Like if I say it's 1, so we're doing the 2 sum problem over this range, right? It's a 2 sum problem over this range. Hold on, let me think again. So we're doing a 2 sum problem for this. It's not necessarily 2 sum because we can still have doubles, right? Let me think again. It will be nice if it's not double. It's just, singular value. So we handle all the doubles in here, right? We handle all the doubles in here, which means 2 times this is smaller or equal to. And then new target is this. And if new target is in counter, then we don't have this. And we simply do it. And we can simplify it in this way, right? So we can just say counter n, the 2 times counter dot get, right? Dot get this thing. If not, get a 0, and then it will just be the same. Actually, I don't like it. I forgot the mod. Yeah, so that's, if we triple, double, we handle it on itself. So now these are singles. Everything has to be single, right? So we say for j in this, and then we say, because we go towards the right, we say while j is smaller than, I'll have to have an n, say n is len nums, okay? So j smaller than n, and we say target. Huh? No, the LeetCode. Oh yeah, no, it hasn't done anything. So target minus n and minus nums j. And we say it has to be, because we do this, and then somewhere down. If it's this, then it's done really. So this has to be, right? This has to be larger, right? Larger than nums j, because nums j is bigger than n. So we want the result to also be bigger. It has to be bigger. It cannot be smaller. If it is smaller, that means we have handled it already. So while this and this, we say if so new target equals target minus n minus nums j. So if new target is in counter, res equals res plus counter n times counter nums j times counter new target mod and j plus equal 1. Right? And then we keep going, and then once if j moves too far, then we just escape. So we run through this, and then we go to the next one, and then eventually we're going to return res. Alright, let's see if this one works. It's a little bit convoluted if you think about it, the whole thing. But who knows, it might be right. 20. Its target is 5. 12. Alright, let's see if it works. If there's anything I didn't consider. So I have array, target, 3, array, target. Alright, I passed this. I'm not sure. I only have 3,000. It shall be good. Actually, oh, whoa, what the hell? Huh? Why would it be not integer? These are all integer. Mod can only be done on integer. Probably this thing. Alright, let's just write it out. 1, 2, 3, 4, 5, 6, 7, 8, 9. I realize if n is larger than, then we can escape immediately. We don't have to keep going. We're gonna be like else we just break. Right? Because if n is larger than target, or larger or equal to target, and that's just no go. So we're gonna do, yeah, let me change this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Always try to make it faster. All right, let's see if it passes. Ugh. Tell me, I probably got it wrong on the same thing. 0, 0, 0. Okay. 0, 0, 0, 0. That should be 1. And I got 10. Okay, how? Oh, the new target cannot be the same. If new encounter and target is not equal to n, because equal to n, we'll be doing this, right? Yeah, that's one line. So if larger than this, if this and, right, and, yeah, I can actually do 0, 0, 0, 0, 0, a bunch of zeros. Let's see how this one goes. Ooh, what the hell? That's actually worse. That's worse than I had in the past. Okay, what went wrong? The answer shall be 680. Right. And of course, 0, 0, 0, 0. That's 1. No, I pass. Let me just copy and paste that. Must have changed the code in the wrong place. Yep. All right, try this one. There we go. So it's the same. I think I got the wrong answer last time in the same one. Let me just take a look. I got it last time. We have 108, 70%. Okay. 923. So first I counter the input array, right? And this way, we only have to deal with unique values. Then I sort the array, and for each number, we check 3 situations. First, if the number, first check if the number can be used 3 times to form target. Then check if the number can be used 2 times, right? And combine with a third value to make target, right? This is essentially a 2-sum problem, right? Finally, check if the number can be used by itself. Number, if a single copy, right? If a single copy of the number can be used to form a target with 2 other distinct values. Yeah, that's it. In the runtime, I'll call it O(n) squared because it's possibly O(n) squared. Yeah, 3 times, 2 times. Important thing is the new one cannot be the whole one, otherwise we're double counting. And then that's 1 time, it's just a two-sum problem. All right, so curious. Huh. Yeah, we got the same thing. Oh, this is much easier. Counter sort enumerate. If A is larger than this, then break. That's actually true. For J in range I, learn vowels. B and C. We have B and C. If C is smaller or equal to 0 or C is smaller than B, then we break. Okay. If C is in counter, if C is in counter, so we have B and have a C. If C is in counter, if A is equal to B, yes, and B is not equal to C. Okay. And if A is not equal to B, but B is equal to C. If A is equal to C, well, this is A equal to B, B equal to C, right? If A is equal to C, this is actually a cleaner. That's the 2 repeats with B and C. That's the 2 repeats with A and B. That's all 3 repeats. This is none of them repeats, and that's O(n) squared. Look at that. I like this one better. I like my old solution better. This just feels a little bit convoluted. This one's very clear, the logic, right? We have for each one, and then we check the same one all the way to the end, and every one we take B and we take C, right? Then we compare if A, B is the same. But if C is smaller than B, then we break. Yeah, that's true. If C is in counter, if C is not in counter, then we just keep going. If C is in counter, then we check. If A is equal to B, but B is not equal to C. Okay. If A is not equal to B, but B equal to C. If A is equal to C, it's A, B, C, all 3 of them are equal. Yeah, I like this one better. What are the solutions? Three pointers. O(n) squared. Counting with cases. Adapted from 3-sum. I think this is what I had. Similar. Okay, yeah, I'm not gonna re-implement. This one is good enough. I mean, we have the same idea, just coded in a little bit more ugly, right? A little bit more ugly than the other one. That's fine. All right, so we're done with this. We need to go back to this problem. All right, so the suggestion is to go for the Z algorithm. All right, so what we saw yesterday was KMP, but KMP doesn't do, so this is a prefix and prefix, all right? You have to find a prefix and prefix. But KMP does prefix and a suffix, and I tried to use KMP for this, but it didn't work. So let's go to Z algorithm, whatever that one is. Okay, so this finds all occurrence of a pattern in a text in linear time. It's the same as KMP, but this algorithm is simpler to understand. It's simpler as Z array. All right. For a string, Z array is the same length as a string, and element Zi of the Z array stores the length of the longest substring starting from str I, which is also a prefix. So Zi is the length of the longest substring starting from str I, which is also a prefix of. So that's exactly what it's asking for. So basically this problem is asking us to create a Z array. Once you create a Z array, you just sum it, and then we have it. The first entry is meaningless. Yeah, the complete string is always prefix of itself, which we just put this one is the total length. 1, 0, 0, and AB3. All right, how do I build this Z array? Okay, how is it helpful? Well, actually, I'll read this later. Well, because the current problem is just to build Z array. All right, let me get Z array. Oh. Man, it's long. So what's the idea? Yeah, O(n) squared, we can construct Z array in linear time. That's what I want. The idea is to maintain. All right, I need a. Let me maximize this. To maintain an interval LR, which is the interval with max R, such that LR is prefix substring. Maintain an interval, which is the interval with max R, such that LR is prefix. If I is larger than R, then there is no, what the hell is I? Prefix substring that starts before I and ends after I. So we reset L and R and then compute new if I is smaller than. I don't understand. Let's just read the code. It'll be easier to understand. So we have n is equal to the length, makes a window which matches with prefix of s. For I in range, okay, if I is larger than R, nothing matches, so we will calculate. We'll calculate Zi using naive way. Nothing matches. So if I is outside, then LR equals this. R minus L equals 0, and starting, so it will start checking from 0th index sample, and I equals 1, the value of R remains 0 and Zi becomes 0. For string, so I is outside the window. If it's outside the window, I start from here, and while R is smaller than n, which is the end, and a string R minus L is equal to string R, and R plus equal 1. string r plus equal, and then string r minus l. What's r minus l? R minus L. It's like the prefix, right? Is L and R is measuring the prefix length. So we do R minus L go to the prefix. Okay, so if it's equal, then R increments, and then we check again. If it's equal, then R increments until a point where it's not equal, right? And then come out Zi, we saying is at I position, right? Current I position. We want to know from I towards the end, right? From I towards the end, how many matches we have, okay? So we have R minus 1. Is that right? Okay, hold on. So we go here, right? And we match, and then R plus equal 1, and we match, R plus equal 1, match. That's R minus, not 1, that's R minus L. Yeah, that makes sense. R minus L is the length, okay. That's good. And then R minus equal 1. Because L and R is marking the longest prefix in I, right? And then we keep moving on I to the next spot. Now I is inside, okay? Now I is inside. So K equals, so K corresponds to the number which matches okay, what's I minus L? Oh, is the number that matches the prefix already, okay? Which matches in LR interval. If ZK is less than remaining interval, if ZK, what is ZK? K equals I minus L, so K corresponds to number which matches in, it's like I is inside, right? As we're saying, I is inside L to R. I is inside L to R. Okay, I is inside L to R. And I minus L is a total number that matches in the front, right? Well, not a total number. It is. And then we say ZK. ZK is at K position. What? K position? Hold on. We go 1, 2, 3. And 3 minus 1 is 2, right? And so K is the total number, right? Not a total number. Because if it's 1, 2, 3, 3 minus 1 is 2, and Z2 is at the second position. So like the same position. Okay, so from second position, what are we asking? What we're asking is, at a second position, I want to see how long we have, right? So second position, and if zk is smaller than r minus I plus 1, so that is the remaining length, r minus I plus 1. So 1, 2, 3, 4, 5. So 5 minus 3 is 2, plus 1 is 3. So from this go onwards, inside L to R, we have 3 left. And if zk is smaller than 3, right? So the total number that have match to prefix at k position, k index, the total number is smaller than the remaining, then that's it. Yes, then that's all we can take. Else, if we can extend more, so zk is longer than what we have right now, else if it's longer, right, which means we can extend all the way to r, and I'm going to start from r and then keep checking. Yes, because from I to r, this part is covered. Yeah, because L to R is a prefix. Remember, L to R is prefix. And we're looking right now at I position, which is inside. And this inside position is the same as the K position from the front. And from the front, ZK has already been calculated. So ZK tell me that if we start from the K position, we have ZK number of elements that's the same as the prefix. So now looking at the L and the R, so start from the I position, I also have ZK. Right? Supposedly, that's the same as the prefix. So if that value is longer than r minus I plus 1, which means potentially the matching will extend beyond r. So what we just now know is from I to r, it is matching the prefix. So we're going to start from I equals, L equals I, and that's true, L equals I, and R, not R, oh yes, R we need to move forward. So that's this part is the same as this part. Holy guacamole. They look amazing. Wow. The Z algorithm. Why is it called Z algorithm? Why does it matter? But I think I understood. Let's see if we can code it up. All right, so this is using Z algorithm. Yeah, this problem is essentially the same. Essentially the same as finding the Z array of S using the Z algorithm. I kind of think those people that finish in like 4 minutes, they did not code everything from scratch. I guarantee you. They look at the problem, they realize what method should be used, they go for whatever their stash. They probably have some algorithm prepared and just copy and paste. Like the Z algorithm, they probably have it, just copy and paste, and then you calculate the total, and that's the score. All right. Let's try to write it ourselves. All right, so we have the Z array. We're going to give it times len s. Now we're going to do n equals len s times n, and we say z0 equals to n. We know, but that doesn't really matter. Oh, actually, it does. It does. It does. Don't do anything stupid. Okay, so now we have an L and R, right? So which just means, so L and R and I, right? So they all mean L and R is the range of the prefix, right? So what we need to find is zi from z0 all the way to zn minus 1. So we say while do we skip on I? I don't think we skip on I. Let me think about it. We keep moving, right? And then once we find it, I just move forward. So I do think I can be, these are 0, okay? And I, which is for I in range, let's say from 1 to n, right? Because we don't, I don't have to stuck at 0. So I is from 1. Okay, so for I is this, so we're gonna check if I is outside R, right? So the current range of the prefix doesn't fit my current value. So now we need to extend, right? We need to extend. So we say LR equals I. They both come to I. And then we're going to check. We say while, right? S. So the current is R. If it's equal to, I need a prefix, right? The prefix. Prefix. Now this is the genius part. R minus L for the prefix. That is genius, right? That is genius. R plus equal 1. So this use R minus I to refer back to prefix. This is genius. So keep going until I cannot go no more, right? And then I can say Zi will equal to R minus L, and then R minus equal L. So because R, we have to go back to make sure LR after. That's the loop invariant. That's the loop invariant at the end of each loop, or at the beginning of each loop actually. L and R demarcates the prefix, the current longest prefix that contains I, right? Else, right? I is inside, all right? So if I is inside, then we need to find out, because that's I is inside L and R, and LR is a prefix. So we need to find out at I's position, what is the longest prefix, right? And then we current LR, we haven't done that yet, so we need to go back to the front, go back to the original, the actual prefix. So we find K is equal to I minus L. So this is the location, right? The index in the prefix that corresponds to I, right? And then we need to find a zk. Zk is at this position going forward, how long it is. And then we say if zk is smaller, should we say smaller equal to? No, it's smaller because equal to, we had a chance of expanding. So we say if it's smaller, then what? Then the remaining length of the R, so smaller than R minus I, right? Plus 1. Then we just say Zi equals Zk, because that's the only amount we can match. The remaining doesn't match. Else, that means we can match the entire thing to its R and this possibility of expanding, right? So if there is possibility of expanding, then we need to reset L equals to I, right? So that's the start of the matching, and R equals to, we can actually say R equals to R plus 1, right? Because it's matching all the way to R. So we can actually say, we're going to set R equals R plus 1. Okay, so R going out And then we do the same thing while SR is equal to SR minus L. Then we say R plus equal 1, and then Z I is equal to R minus L, R minus equal 1. Right, so we do this. Once we're done, then return, say sum Z plus N. Index out of range. Of course, because we forgot R has to be smaller than N. R smaller than N, and oh wow, it does pass, huh? Does pass. But it requires the algorithm. Alright, let's do. Always want to do this. Wow. All right, so we're done. So basically, all right, if you know about Z algorithm, this problem is not difficult, right? This problem is not hard. But if you don't know, it is very challenging to figure out the Z algo. So in Z algo, we have LR, right? That maps to the LR that we have indices LR that marks a window in which contains, right? Which contains, this window contains the longest, right? The longest substring that is also part of the prefix at the moment. I is the index of the letter currently under consideration. Now, if I is outside the window, then we have to compute the window, right? When we have to reconstruct the window, because it's outside the current window, there's nothing the window cannot help. So I have to reconstruct the window. Here is something ingenious. We can use S R minus L, right, to locate the letter in the prefix. Can locate the letter in the prefix. So in other words, we only need to increment R, and we can make direct comparison between SR and its corresponding value in the prefix. Now, if I is inside the window, we need to find the corresponding prefix letter. I'm going to find a prefix letter, right? A prefix letter, prefix position that corresponds to I in the current window. We call it K, and k equals I minus L. From k, we can obtain a zk, right? Zk, which is the longest length substring prefix, right? Substring prefix that starts from k. So if zk is smaller, right, than the remaining length of the window, that is r minus I plus 1, then from position from I, we at most can match, can have a substring prefix as among the same length, right, as zk. Otherwise, if zk is larger or equal to r minus I plus 1, all right, that means there is possibility of extending the prefix sum, not prefix sum, extending the substring prefix starting from I beyond R. In this case, we set L equals I and R plus equal 1, and search from and search again, right? Search again. Yeah, and search again. And it's on. Okay, it's on because the initial search is on, and then we come back here, and then we will do another search. But each search, right? Each search, every time we do search, is always go beyond, right? Each time we do the search, always go beyond. Now this is on because each time we search, it's always beyond the current R, and each I, yeah, this means each position in S at most is visited twice, once by the search and the other time, and the other by I. 532. All right. I think there'll be a lot of unhappy people. Z function, yeah. Well, can you use polynomial rolling hash and binary search? Now, this is just a Z function. You just need to know Z function. Oh, I guess you can. You can do KMP. Count the number of times each character appears in a prefix. Wait, how do we do? I tried. I tried a KMP yesterday. It didn't work. And a count array. And then we use the count array to count the number of times each character appears in a prefix. Summing up count will give us the length. Number of times it appears. So we add each position. Wow, that was a very fast way to do LPS. Count j minus 1 plus 1. Or j, what's j? J is ending this. What's the longest? Yeah, what's the longest suffix that's equal to the prefix? So have a certain number, right? And then we say j minus 1. J is this count. J minus 1. What? Count, what's count? Count is the number of times each character appears in a prefix. Okay, so this is the number of times appears in one prefix, two prefix, three prefix. That's true, that's true. So, and then we go j one by one, right? And each one, if j is 0, then we just push in 0. Because this one does not appear in any prefix. This is a length of 0. If at this position, that'll have certain lengths, okay? Then we say at this position, the number of times it appears in the prefix is this one, plus 1 is the current one, okay? Oh, that's very smart. Yes, so j minus 1, all right? J minus 1. So if my count is 4, right, then j minus 1. So j minus 1. Hold on. I just odd and then I realized I didn't quite understand it. J minus 1. So at a certain position, and we have that length, right? We have that length. And the length minus 1 is a smaller length. And we're looking back to count 3. So how many times this one is involved? How many times this one is involved in a prefix? This one's involved in a prefix. And it's limited, right? So this one's involved in the prefix certain number of times, and then +1 because I have a new one, right? A new prefix involved. So the count is at each position is the number of prefix that the current letter belongs to up to this position. It doesn't extend. Is that right? B A B A B B. One, two, three, 4, 5, 6, 7, 8. Hold on. 0, 1, 2, 3, 4, 5, 6, 7, 8. Position 8. I think they got wrong. I think this means this position. So this position appears in B, BAB, and BA. BABAB. Let's appear in all prefixes. Mm-hmm. This one is a bit tough to understand. And this is the count. And it didn't make any sense. We say we count the number of times each character appears. So if a character appears in 3 prefixes, what does that mean? Exactly, what does that mean? And sum them up will give us the length of all prefixes. So if one is in 3 prefixes, and this one, let's see, like this is in 3 prefixes. How does that help? We're in this, and we're in this, and we're in this, right? And the one before it said we're in this, and we're in this. I don't understand this LPS. To count the number of times each character appears in a prefix. So I know how many prefixes each character is in. This character is in, let's say, a certain number of prefixes. And the next character is in a certain number of prefixes. I think it's polluting my mind. I can't figure out. Do I have another LPS? And that I cannot understand the LPS. And I choose not to. Polluting my mind. Good question. Is this like a namesake? Oh yeah, the third one is kind of, I still remember. Interesting. Z. I forgot wrapping cap. I forgot wrapping cap. I still don't know. Okay, it's fine. Right? If you don't know how to implement it, it's fine. We can always look it up in a contest. But you need to know that there's an algorithm that exists. Like, I need to know KMP is doing this, and the Z index is doing this. The Z index is Z function. What does robbing carp do? I have to read robbing carp again. Alright, that will be it for today. I will see you guys tomorrow. Adios.